Can I get started?
Yeah.
Okay. So before I start everything, I want you guys to feel better because you have a lot of questions, with you for this lab, and you'll go and leave and with more questions. So this is what usually happens for the op-amps. It's just a black box. You just need to learn how that works. You need to dig very deep into it, like why is virtual short, why the non-inverting inverting equals to each other. I can show you something really quick, how you can really deeply understand what's going on for the op-amps. You have to build an op-amp by yourself first, not using the op-amp in like what you're going to do in this lab, but build one. The chip you're going to use, like these ones, and design one chip and send it to like MOSIS or TSMC for fabrication and get a chip of your design, so you understand what's really going on inside, right? So I'm going to show you really quick how that looks like inside really quick. And this is still just a microelectronics one, right? If you want to learn the details about it, it's going to be a graduate level microelectronics 2. But you can see that the op-amp, is that here? No. DSpice, future accelerator, deregulator layout, unwell, unknown thing like GBSI. Things here. 5. Let's see. There's something like this is the op-amp, and this is not the only version of op-amp in the world, right? It's just the CMOS version of it. You can build it using BJTs, but this is a CMOS version. The PMOS and NMOS is a differential pair. You got all these tail current. These are and some offside voltages and the final stage of amplification, and you have to learn a lot of AC signal magnification or amplification or small signal analysis for these transistors. It's really annoying if you don't know what's going on in here, but just being told that they are equal. I hate it. When I was in school, I'll let you know, before I get into my PhDs, where I finally got a professor told me how op-amps worked. But I learned analog, which is 300 class, not even circuit 1. We didn't learn op-amp in circuit 1, but I didn't, really, I was not very serious about circuit 1 as well when I was in my second year in college. But they didn't cover op-amp in circuit 1. And when they covered op-amp in analog, and they didn't tell you like what's inside. So until when I was in UNLV, my professor is one of the most popular analog person in the US or in the world probably. He wrote a textbook I'm still using right now. So we got a lot of opportunities to build op-amps on the chip level. So you use LT-Spice to run all of the simulations, and it's just a basic version, but there are so many other versions to boost the gain, boost the bandwidth. There are so many techniques you can use to change it, to improve it. And so the one was here, the second year I got to FLC, we actually got a chance to fabricate. So this is the layout, the chip layout. These are just transistors being fabricated on the silicon wafer. What's actually inside the package of the chip? I couldn't see for a whole life. If you don't attend this lab today, my section, you will never see this kind of thing for a whole life probably. This is the internal view of the chip, and these are P-type transistors, and these are N-type transistors, and these are just metal wires. It's metal 2, metal 3. This is metal 1, metal 2, and the yellow ones are metal 3. And then eventually you design, this is a capacitor in the chip. Could you believe that? There are just 2 polysilicon layers on the top of each other, have overlap, so you got a dielectric material in the middle. You got 2 plates and form a cap. You can only modify the area of the cap to change the capacitance. And you can see this is the one op-amp. Physically, will be printed on the silicon wafer. It looks so different from the triangle shape. And I just mentioned this is the op-amp, and this is the final amplification stage. And this is the one capacitor. If you look at schematic, thing I want to let you guys look at this one. Here, right? That's a cap. That's a capacitor in the schematic. And these are the rest of the circuit. But if you look at layout, the physical layout, which is what's actually being printed onto the silicon, it looks like this. So the capacitors are huge. So can we make a 1 farad cap in the chip? Probably the entire chip is nothing but cap. So farad is a very huge unit. That's why when you are dealing with capacitors, it's usually like 1 microfarad. Is 1 microfarad a big capacitor or small capacitor? No, it's huge. It's huge. Yeah. But for for power electronics, like all these power grades, probably 1 microfarad is not that big. But for whatever we are dealing with on the bench, 1 microfarad is a big capacitor. Okay, for integral circuit design, whatever being fabricated into the chip, like all these ICs, they are in picofarad level, like 20 pico, 100 pico. So 1 micro is actually a big capacitor. What about nano level, nanofarad level capacitors? Still pretty big actually. If you build a 1 nanofarad cap on the chip, it's a big capacitor. Okay, and this is the entire look of the chip. I have 1 op-amp, 2 op-amps, 3 op-amps. These are just the metal wires being connected to the ground. I just want to make it big so they have a solid ground. And these are just some of the logic gates. This is the 1 inverter here. The scale of this chip, it's a little silicon wafer in the package. And it's just 1.5 millimeter for each set here. So it's 1.5 by 1.5 millimeter. All right, it's a little tiny chip. And you can integrate, by far like 1, 2, 3 op-amps. But I can see maybe can fit, another 10 here. And so we can eventually get like 30 op-amps into that area by using this 40-year-old technology, the super old technology we used in 2018. So the one we are using for my senior son right now is 180 nanometer technology, which means the smallest transistor length you can fabricate into the wafer is 180 nanometer for the length of each transistor. For these ones are 600 nanometer for each transistor, which is 40, 50-year-old technology, but the 181 is a 2005 technology. Used to be super good and popular. Right now, it's still one of the most popular technologies being used. Doesn't mean it's the best performance, but just because it's very cost effective, it's cheap to fabricate, and it's not that big, not that small. It's just okay, all right? Still the most popular one, the one we are using right now. And the most advanced technology right now available, okay, from TSMC, a couple years ago that was 7 nanometer technology, which every single transistor can be fabricated into like 7 nanometer for the channel size. And most recently, I think the 5 nanometer technology is gaining some momentum. It's available commercially, most recently, I think probably from last year. And 2 and 3 are still being developed. I don't know when they will be available, but it's reaching the limit right now. So this is schematic as the layout. Right. Okay, the goal to tell you is what's inside the op-amp, and don't feel bad if you don't know what's going on. It takes time to digest or absorb what I'm saying, because what I'm saying is directly from my brain. So they're already registered in my brain. But you guys have nothing in there right now. You have to digest it, have to repeat it, and learn it through hands-on experiments on the bench. Make sense? So it's okay if you have so many questions and even leave with more questions. But I will try to answer all of them as much as possible. Okay. So first, why do we need an op-amp or amplifier? Why do we need it? Seriously? You don't know why we need to amplify? Yeah. sorry. Okay. That's a good excuse. Yeah, that's right. Yeah. So the signals from sensors are most of the time are tiny, like 10 millivolts or something. So before you fit it into where, right? It's another question. Before you fit into somewhere, and you need to amplify it. Okay. So what is that somewhere? What I'm talking about? Do you have some big picture about like the entire workflow of the signal handling? So for example, you need sensors, right? So sensor to do something. That's the final goal. Like temperature, humidity, and sound, or like anything. There are sensors. Recorded. Let me check the audio. The audio works great. Okay, and the sensors will convert the signal from the analog world into what usually? Hmm? No, sensor. Oh yeah, that's right. But if it's to digital, then we don't need op amp anymore. Because op amp is amplifying analog voltages. So it's like you got a sensor signal, right? Sensor signal can be tiny, only 10 millivolts. Okay, but you have you probably haven't heard about this kind of thing. It's called ADC. It's analog to digital converter. So this thing will convert all the signal into one and zeros. So take my CE 241. This is one of the options in your BSE map, right? If you take this one, you'll learn a lot of good things from me. So you understand like what are digital signals. Okay, so convert analog signal to digital signals, and then so you can register all the data into memory banks in the computer. That's how that works, because we eventually need a computer to process everything, and the computer only stores digital data like one and zeros. So how you convert whatever temperature into one and zeros? You need an ADC. So ADC will do the job. Analog to digital converter. That's why you talk about like into digital, right? You need the ADC to convert the signal to digital, but this one has a range, usually 10 volts to 0 volts. But if you only convert a small voltage like that, you are not fully utilizing that resolution of the ADC. You want to amplify to the full range so you can, fully utilize the dynamic range of the ADC. So that the ADC just divide the signal into like millivolts ranges, the little steps, so they can resolve the changes of the analog signal and then convert into digital signal for each point. So this still can be confusing since you haven't done that before. But just want to let you just remember that you need to utilize as much as the range, the dynamic range of the ADC. But your signal can be different, like can be tiny, can be huge. Sometimes you have to shrink it, but that's rare. But sometimes you have to amplify it most of the times. In order to do what? In order to use the dynamic range of the ADC, right? Okay. So, but you have small signal, but you need to, you need a bigger signal swing for the ADC. So you need an amplifier in the middle. Does that make sense? So it's an analog as a sensor to op amp and then to ADC. And eventually ADC will send a digital signal to the computer to register all the data into the memory banks. Make sense? Doesn't make sense? Okay. Cool. All right. Okay. Is that fascinating? Just think about this, it's just everywhere. Like even for the whatever I'm doing right now, I'm recording my lecture. I have a little microphone here. It receives my voice as a analog signal, but eventually it bounces that what kind of like actuator inside and convert my voice into an analog voltage. But that can be tiny, can be big, can be strong, and then we have to pre-process it, right? Or pre-amplify it. So the ADC inside my computer can digitize it and eventually register the data into the memory bank in the computer. Okay. So that's why we need op amps. Op amps role is in here. It's amplify the analog signal from the real world. And this is the annoying shape of the op amp. Confuses generations by generations. All right. Surprise. So this guy has a property which is called open loop gain. It's we labeled as AOL open loop gain. OL, right? Open loop gain. It's called open loop gain, so which means we don't have any feedback to it. You'll see what's the feedback. There are just so many terminologies, and it's annoying for beginners. It's very, very, very annoying. So don't get frustrated. It's okay. The good thing is I'm recording it. Open loop gain, new concept, number one. Okay, open loop gain. VP, okay, P positive, VM minus, plus minus, right? V plus, V minus. And this is V out, okay? So V out equals, if I don't have any feedback, equals VP minus VM times AOL. So what is AOL? Open loop gain, concept number one. You're thinking, why is this important? You'll see. And this one ideally is infinite. For example, 1 million. No, so oh, 1 million, just 1,000K. Okay, so it's huge. But you only have a real-to-real power supply, for example, 5 volts. Why we like 5 all the time? Mm-hmm. Yeah, why is it like 5? You got 5 fingers. That's usually how that works. Yeah, why 3? Since you are not patient enough, after we count to 3, we are losing patient. That's it. How many drops do you want? 5. Right. Okay. The power supply only supplies 5 volts, and open loop gain is huge. And if you have a tiny difference, let's don't talk about like 1 volt. What if 1 millivolt? So this guy equals 1 millivolt. So what's going to happen? What's the result for VL? 1,000 volts. To have that power supply to support that. It's going to saturate at 5 volts for the output. Distortion, we'll talk about that later. But now it's just like if you have a difference between these two terminals, it is able to amplify like crazy. And this structure is not useless. You are going to use it actually for the little car project in the future. Actually, the lab after next lab. So you need to do that. So this is called comparator. So it uses the infinite open loop gain of the op-amp to compare these two pins. How that works. For example, if VP is bigger than VM, what's going to happen? This will become a little positive thing, right? Like 1 millivolt or something. Immediately, it's going to amplify the input voltage to 1,000 volts. It's going to saturate 5 volts, so you are getting 5 actually. So if VP is larger than VM, you're getting 5 volts. If VM is larger than VP, you're getting a little minus thing, minus delta V, but it's going to saturate 0 volts, which is ground, because you don't have that negative voltage supply. So the lowest voltage you can support, which is 0 volts, for the whole system. You're asking like, why is this supports the limit for the VL? They are not connected. This is another thing like frustrating people. So keep in mind, so you haven't designed that thing yet. You don't understand what are top and bottom rails. Just remember it, okay? So this one, so the plus the power supply, the 2 power rails. So that's the top and bottom rails, the 2 power rails, defines the levels, the upper and lower limit of the VL. Keep in mind. Okay? So if VM is larger than VP, which means this minus this will be a tiny negative delta V, and but times a million, you are getting a huge negative delta V, but it's going to saturate at no, 0, yeah. So it's comparing these two terminals, right? If VP is larger than VM, you're getting 5. If VM is larger than VP, you're getting. So if I plot it, Okay, so for example, Vm equals 2.5 volts. Vp is a triangle wave. Okay, let me plot it for you. 2.5, that's Vm, V minus, and Vp oscillates. So my question is, what is V out? Think about it. And I'm going to find someone to draw it here. Give you 2 minutes. So this is Vp, right? Okay. And this is 5 volts. So when Vp, this is Vp, is lower than Vm for this period, this is time, okay? When Vp is lower than Vm, you are getting 0. But once this approaches this level, which is Vm, 2.5 volts, once Vp is reaching that 2.5, so they are equal and but slightly larger than Vm, Vp is slightly larger than Vm, you are getting a tiny positive delta V and will be amplified like crazy to 5 volts. Then it's gonna jump. Starting from here, jump to 5 volts. And then because Vp keeps above 2.5 for this period, it's going to keep until here. Whenever Vp is slightly lower than Vm, it's going to drop. Okay? Who can draw it here? Just do whatever I just drew on the paper. Who can do it? I'll let you draw on the paper for 1 minute. Okay? 1 minute from now, I'm going to randomly pick up someone to draw it here. We can help each other. If I can do it now.
So what we are doing? Do we have like such sort of numbers?
So Vm is 2.5, okay, and Vp is oscillation. So you're supposed to draw V out.
Okay. Yeah.
Vm is 2.5, Vp is triangle.
Okay. So it's gonna go like this.
Yeah. Yeah. So what's V out?
5.
Okay. That's right. Good. Good catch. Make sense or not?
And VP is the triangle, right?
Yes.
So VP is essentially VN, right?
Mm-hmm.
Okay.
Yep.
So like depending on the
Yeah.
5 or 0.
Good question. Let's do this.
So VM is a threshold.
That's right. Someone draw V out for me this time. Oops, sorry. That makes sense to everyone? Kind of. Okay. All right. This will clarify a lot of things, right? Because you got confused, like why it performs like this sometimes, why it's amplifying an analog signal, because you don't have any feedbacks. That's why it's a comparator instead of amplifier. Okay. What's the name of this circuit? Comparator. Is it comparing? Yeah. Like this is large, you got this. Is this large, you got this. It works. It's a binary result. Okay. So what if you want to amplify something instead of just getting a 1 zeros? Right. So this is a digital data. The first time you get a digital output like 1 zeros. Okay. So what if you want the output to be a continuous voltage instead of just 1 zeros, just oscillating like crazy? But you want a continuous smooth sine wave just to be amplified. Like you got a small sine wave and output a big sine wave, right? That's an amplifier, right? So you still use this topology. And I think the first couple examples in the let's don't involve that first. Let's just don't consider the reals first. All right, so this circuit is called inverting configuration. Why is this different from the comparator? What's the difference? What's the main difference? I know it's a lot different from that one, but what's the main difference compared to comparator? What's the main difference? Has a feedback, which makes a difference. Okay. Yeah, it has resistors over here, which is providing a combination of gains. You can modify the resistor ratio to find a gain, but I'm going to show you how to calculate it very quickly. But now there's another that's concept 2, right? Step 1, I'll label it so you know which parts, what are the concepts that are confusing people a lot. Concept number 1, the open loop gain is infinite. So like 1 mega. All right. Don't ask why, right? Stop there. It's just huge, right? Huge open loop gain, which makes comparators output to be like either 1 or zeros because it's saturating the op-amp. Okay. The confusing concept number 2. If you do a negative feedback, then VP equals VM. Grab 90 from 100 electrical engineering students from CU Boulder, and 90 of them won't be able to tell you why. And grab 50 to 60 out of 100 from Stanford, MIT, they won't be able to tell you why. It's just so frustrating. That's how frustrating that is. So don't feel bad if you couldn't get it now. Okay. But I have a way to explain it. Okay. Hopefully you can feel the circuit physically. I don't know if you can do that now, but let's see. If, because the open loop is huge, no matter how you connect it, okay, since you have a negative feedback. So think about that. So the VP minus VM times the open loop gain is still valid. Okay, still works. That's still valid. Sorry, still valid. And so VP minus VM, for example, they were not equal at the very beginning. And because the open loop gain is huge, it's going to amplify that like crazy. Okay, will give you a huge voltage or a trend to increase VL very, very quickly. But however, because you have V minus here is like a little bit low, that's why this one will dump a little current in here to charge it up and to make it equal. because of negative feedback only, and they're equal. If you just grab an op-amp from the drawer, are they going to equal? No, they're just two different terminals of op-amps. It won't be equal. You have to do some sort of negative feedback to make it equal. And 99.99% of the time, you are using negative feedback, never positive feedback. If you do something wrong, your mom should tell you, no, that's wrong. Doesn't like you do something wrong, your mom encourage you, do more about it. It's going to keep going and then saturate. It won't work. Yeah. Did you feel that? I'm going to say that again. Okay. So for example, VP, I know it's ground, but assume there's some kind of noise, right? To make VP larger than VM, right? So VP minus VM times AOL will be a huge VL, right? It won't reach a huge VL because the negative feedback is light chance just moves so fast. It tries to move up. But whenever it moves up a little bit, it's going to dump the current here because there's a connection. There's a connection. That's why it's just feeding that one back here to keep them equal. So here's an interview question, right? Very quick question for you guys. So during the interviews, some of the recruiters ask you like, why the op-amps VP and VM are equal? Why? How do you answer that question really concisely? And 2 points, right? 2 bullet points. Why the op-amps two terminals are equal? 2 bullet points. First, because of the negative feedback. Second, because of the infinite open loop gain. So you guys are still digesting this, okay? Just try to seal it in your mind. That's what you need to know. Outside of this class, this is one of the outcomes. You need to seal this in your mind. Sarah, what are the 2 bullet points? Infinite open loop gain, all right? It just works because if this like I told you, right? Because if this is larger than this, it's going to amplify the signal a lot, and then it's going to dump because you have a connection here. It's physically connected even through a resistor, but still it's going to dump current in there. But because the electrons move super fast, so you won't get a chance to move high. So it just move a little bit higher than. So when like 2 points, you know what I mean? So the vice versa. So if VM is larger than VP, what's going to happen? So you are getting a super negative value, right? I know it's not going to negative since you don't have the power supply, but it's going to go down, right? And then it's going to dump current in here to pull this down to make them equal. That's a magical feedback always, which is a very good thing. It's just not in circuits, it's everywhere in the country, in the government. You need feedback. So, yeah.
If the open loop gain AOL in the first one without the feedback loop, that you said that in the very first example. Yeah. You said it's comparative because it's multiplying it by 1,000,000. But is there a value of the open loop gain where it's not a comparator, will it still show some of the waveform instead of just smacking up and down?
It has to be super tiny signal because the gain is huge.
The gain's always
huge. It's internally when people design it, like what the circuit I showed you. Yeah, the circuit I showed you. All the transistors has that property to make it large, and which is desired. We need it to be huge because we need these ones to be like. So that's why they call it. Okay, concept number 3. VM, VP are virtually, this is very annoying, virtually shorted. I'm not saying the technology is annoying, I'm just saying like learning all these nonsense concepts are super annoying for beginners. VM, VP are virtually shorted. How that comes? Because they are equal, that's why they are virtually shorted. And concept number 4. No. Concept number 4, VM is virtually grounded. These are actually similar conclusions. Okay. Can I go through this real quick and see if that makes sense? Because there's a negative feedback, because the open loop gain is infinite, so VP equals VM. So VP and VM virtually shorted. And because VP is grounded, so that's why VM is virtually grounded. Could you do the same thing? From the very beginning, Sarah. The challenge. So start from the beginning, okay? What's happening here? Mm-hmm. Mm-hmm.
And VP virtually shorted.
Mm-hmm.
VP is grounded, that's why VM is virtually grounded.
Nice. Did you get it? Does that make sense for everyone? If it doesn't make sense, it's okay. Try to memorize it, seal it in your mind, at least to prepare it before the job interview. I'm gonna upload it to the lab's Canvas page. Anything else you need to know here?
So changing RF, the value of RF, changes the gain.
The closed loop gain, this is another thing. And let's do it next page. Okay, so the open loop gain something is, we just done for the open loop gain same stuff. Right now, let's talk about the closed loop gain. Which is the gain you're going to use for this lab. Because of the open loop gains, negative feedback, and because of the, all the properties derived from these two properties or, techniques, so we can use our op-amp in a closed loop form to amplify analog signal into a continuous analog signal. Okay, so now start from this page, forget about open loop gain and everything. Now let's just use it as op-amp, all right? So this is an inverting configuration. 5 volts. I know this is let's just put it like 5 volts here for now, right? So I have 2 power rails, 5 volts and negative 5 volts. And closed loop gain. So what is the gain? How much I can amplify VI into VL. How that works. So another thing you need to know, so the current, I call it I0. Concept number 5, annoying as well. I0 equals 0, which is the current that flows into the op-amp is 0. Because if I don't tell you this is frustrating, I just keep talking about everything. Right now you are already falling asleep, I think. It just at the very beginning it doesn't make sense, and another thing doesn't make sense, and you're just stacking up, and all the things doesn't make sense. You just feel like you don't want to stay here anymore. So I0 equals 0 because if you look at it has a very high input resistance. You don't have to dig too deep into it. So this is the VP and VMs into the NMOS transistor's gate, and the gate is a dielectric material. It doesn't have any physical connections. It's a huge, like, mega ohms of input resistance. It's using VP and VM's voltage to provide electric field to attract electron holes to the channel and then conduct current. But again, just let you know what's happening, but you don't have to dig very deep into it. Now, concept number 5, you need to know the current flows into the op-amp is 0. And it's confusing people further because if there's nothing getting to the op-amp, why do we need the op-amp? Really small, yeah. But we consider it because it's not ideal, right? If it's ideal, it should be 0. So why do we still need it? We need the voltage in it, but why the voltage is being manipulated and amplified if it's just like there's no current getting to there? The op-amp provides the current to where? Here, yeah. So for example, if we don't have this op-amp here, we don't have it here. We got a VI resistor, right? No, I just don't have it here, okay? I remove it. And then just skip it and directly get into VL. I got RF, I got R1. Could you amplify VI and get a bigger VL here in terms of amplitude? So VL is something like you have a load here, right? Like 1 mega ohms, for example, and connect to the ground. And VI is also grounded, right? So I have a ground here as a circuit, formal circuit. Because there's nothing getting to the op-amp, so I just remove it. I just remove it. Could you amplify it? It's just a resistor network, but nothing else, right? Can you amplify VI? Why? Yeah, it's a voltage divider. It's a voltage divider. You are dividing VI. There's no way to amplify it. So why you put something here which doesn't accept any current, but it's amplifying the signal? Why is that? Let's still look at this resistor network, okay? After you put a op-amp in here, what's happening is you virtually grounded this point or this point. So you drop this voltage, abruptly into 0, a sharp drop to 0 volts. Okay, so just drop it down to 0 volts. And then because this is a resistor network, it's gonna keep flowing to here. You got a 0 volts here, and the current flows into that way. So it's actually boosting VL if you drop it really quickly to ground first. It's changing the phase, but it's okay. It's changing the phase, but it's actually increasing the voltage. That's the only way you can do it. You have to drop it to 0 first. So the op-amp uses the virtual shorting property to virtually short this point to 0 to ground. In that way, you have a pretty sharp dip. And then because the current is not going into the op-amp, so this is the only way the current can flow, right? So the current flows, I know it's dropping the voltage further, going to the negative range, but the amplitude is larger. You know what I mean? So you have a 0 volts. So the voltages are relative. So if I'm asking like, there's a minus 20k volts, you are saying, hey, this is tiny. I mean, 0 volts is way bigger than negative 20 volts. Is that right? 20,000 volts. So if you are trying to, someone asks you to touch 2 wires. One wire is grounded, 0 volts. Another wire is negative 20,000 volts. Which one are you gonna touch? 0, right? Negative 20,000 volts is not tiny. It's just oscillating to the swing to the other terminal, other polarity, but it's huge voltage. According to the amplitude, right? It's huge voltage. The same thing here. You are getting a negative voltage, but you are amplifying the magnitude because you can have a bigger RF and this is load, right? Don't consider that for now. If RF is larger than R1, you are getting a larger VL compared to VI. So how do we derive the gain, voltage gain here? Okay. Keep in mind, current flows in and won't get into the op-amp. This is the only way the current is going to flow until VL. That's where the current flows. So this is how you derive your voltage gain. So this is 0 volts, right? Virtually grounded, 0 volts. Make sense? So I got a current here. This VI minus 0 volts over R1. That's a current flowing through this resistor. Is that correct? Okay. Because it's not going here, that's why it has to go up. And so 0 volts VL. This is just one current. It's not changing. So that's why VI minus 0 volts over R1 equals 0 volts minus VL over RF. And then you got VI over R1 equals minus VL over RF. So VL over VI, which is the gain, equals minus RF over R1. So that's how you amplify your V out. That's a closed loop gain. Start feeling tired and not making sense and just feeling frustrating because you don't understand what's going on inside, right? That's always what happens. I'm trying the best. If I were you, I would fall asleep. It doesn't make sense at all. I hate it, right? But it's useful, so let's learn it. Any questions by far? Just ask.
Okay, so once it starts amplifying,
Okay?
we're not gonna have a current flowing in a positive direction.
No. No.
It's gonna feedback.
Yes.
Okay. But we're just using that current that flows through the top as a way to calculate the gain.
The current actually flows here.
The orange path.
No, the signal. This VI is the signal. The signal's current flows in here.
It flows through there?
Yeah. That's how it's getting amplified.
Yeah.
There are a lot more things about it. But I will let you know this is fascinating. You know why? It's in your pocket. Grab your phone. What's in your phone? Camera. Okay? So if you connect this guy in this shape or in this configuration, and this is photodiode. You see, working in the opposite direction, the opposite way of the LED, right? The photodiode receives light and will generate photocurrent in that way. Okay, and then the photocurrent being converted into voltage, so you're getting a voltage signal for the environment. So you get a pixel. So this is called TIA. I know it's called inverting op-amp, right? It's an inverting configuration because the signal goes into the inverting terminal of the op-amp. That's why it's called, this is another concept. Yeah, it's just super annoying. So it's inverting configuration, inverting op-amp because the signal get into the inverting terminal of the op-amp. However, this is a current to voltage converter. It doesn't amplify voltage. It's another thing. Like you got a gain, it's amplifying the voltage. But actually, physically it's not. It's amplifying the current into the voltage. That's why it's called TIA, transimpedance amplifier. It converts current into voltage. That's why we use it for every single pixel in the camera. You got a photocurrent, photodiode. You shine light onto it, then generates photocurrent, which will flow through here to ground and create a voltage drop, which is V out. Depends on the intensity of the light, you got a different voltage. That's why it's the intensity of the different intensity of the pixels.
The current comes out of the op-amp?
No, current comes out the physics, the electrons in the photodiode. Einstein got the Nobel Prize for the photo effect back in like 1930s, I forgot. That's why we got a camera like works, because the Nobel Prize fundings from there. Including this little guy here, the document camera, right? It's still using Einstein's technology. It has the TIAs in here, definitely, for each pixel. you have this guy here because you are using the infinite open loop gain, and these two are virtually shorted. That's why this point can be dropped sharply to 0 volts. That's how you get a gain. Because you only have, if you remove this one, you only have the resistor network. It's only dividing the voltage, not amplifying it at all.
So can you say that we are using the voltage inside to gain the voltage instead of dropping the voltage?
No. So this one, this inverting technology, the inverting op-amp, converts current into a voltage. Okay, this is another point is confusing people. You got a voltage input, but why you're converting a current? But actually the voltage is being converted into current because you got a resistor here. Okay, so the voltage is being converted into a current already, and it's amplifying that current by RF over RI to a V out. But also from the other or different angle, you can say this amplify VI by RF over RI, R1, which is fine. But physically, it's not a voltage amplifier. It is able to amplify voltage, but fundamentally, it converts current into a voltage because it amplifies the voltage VI by converting that VI into a current first, and then amplify the current into a voltage later.
How much current comes out of these cables?
Same current. It's not changing. See, I use this is the current. Same for the two sides.
So it's the same current, it's a different voltage. That's coming off of
That's why we got a different resistors which will give you different voltages. That's where we got a gain.
so it's really low current still, like high voltage.
Mm-hmm. Yeah.
But the same current, always the same current as the input.
Yes. So there's just one current in here. No, there isn't a second current in here. So I'll give you another example which will be more intuitive. Okay. So what if I don't have the R1? What about this one? Is this going to work? It's going to work. You just don't have the R1 here. It's fine. So current is going to flow here. And this is a really ideal TIA, transimpedance amplifier. TIA, only for the inverting technology, not the non-inverting technology. I'm going to introduce the non-inverting pretty soon. Okay, so the inverting technology, yes, you can amplify a voltage, but actually converts the voltage into a current first, and then the current is being amplified or being amplified or being converted into the voltage later. Okay, it's like voltage current, current voltage, but eventually it looks like it's a voltage amplifier, but it's not. This is how it works. It amplifies the current into a voltage. So if someone asks you, what's the gain? What's the gain of this TIA? No, you don't have anything here. What's the gain of this RF? Oh, of this, I told you. So it's going to be RF. The gain is RF. Whatever you have here, usually the resistor here will be huge, since the current, the photo current is tiny, like 1 microamp. So what if I have 1 mega ohms? It's a real world resistance. Like when you amplify the photocurrent from a pixel, you actually use 1 mega ohms a lot of times. So what's the gain? How much is the gain for this TIA? No, where's R1? You don't have R1. What's the gain? It sounds weird, but the gain is 1 mega. But you are thinking about, hey, gain must be like VO over V1. You don't have V1.
We don't have R1.
You don't have R1.
But that's in the denominator, and that's a 0.
No, you don't do that because you are not amplifying a voltage right now. Now you're amplifying a current. So eventually what's happened, for example, this is I0, okay? So VO over I0 equals what? Yeah. Output over input is a gain, even though it's a current as input. It's fine. That's how they define the gain of the TIA. So that's why the TIA's gain is just RF. It can be huge a lot of times because the current usually is tiny. Okay, so now you know an inverting op-amp can amplify a voltage, but it's basically a TIA. It amplifies the current. So what if you feed the signal to the non-inverting terminal?
You said it's only a 1% scenario, right? You said non-inverting?
Yeah, non-inverting. You have to do it in the lab. So I'm going to introduce it. So for the non-inverting, signal comes from the inverting terminal. So the inverting terminal has an input connect to it with a resistor, right? That's an inverting configuration. But if you feed the signal to the non-inverting terminal, which is the plus terminal, it's called a non-inverting topology or configuration. They're asking, like, you're curious about, like, why you still have to do this? Why you don't do this? Why this is wrong? Well, I couldn't even tell the difference. What's the difference? Why? I want to feed the signal to the non-inverting terminal, so this is non-inverting topology. And this is also feeding the signal to the non-inverting terminals. It's also a non-inverting topology. Why this is wrong? Like I told you, you only do what? You only do what kind of feedback? What about this one? Yeah, it's feeding to the positive terminal. It's a positive feedback. Never do that. 99, only 99 point, or only 0.0000, I don't know, only 1% for some of the applications, which is odd. I have never used it, but use this positive feedback. Never use it. Probably will never use it in your life. Don't do it. So still have to feed it back to the inverting terminal. Make sense? The signal is in the non-inverting terminal since this is a non-inverting configuration. How to calculate the gain? VI is the input, right? VI right now is here, is at the non-inverting terminal. Because of what and what, these 2 points are equal. Sorry, I'm just repeating. Can you repeating myself? What? Because of what and what, these 2 are equal. Justin.
Because it's negative feedback.
So what's the voltage here? Yeah. Make sense? Okay, now let's calculate VL. So you use so there's nothing, so it's not getting into the op-amp, right? Current is not getting into it. Again, all right. So even though it looks weird, but you know the ground, the current flows like this. Yeah, it can flow from ground. Just depends on the potential. It varies, so sometimes can be lower than 0 volts or higher, doesn't matter. I just define the current direction like this, can be back and forth over time. Okay? Which one? No, VI is not going to 0. VI is VI. I? Oh yeah, it's not going to be 0. Yeah, sometimes probably, yeah, can be. It's oscillating. This is the AC signal, right? Now let's calculate using Ohm's law, okay? So 0 volts, right? So 0 minus VI over what? R1 equals VI minus VO over RF, right? VI minus VO over RF is the same current. Then move this to here, move this, move this here, right? So you're getting, can I do that? Yes, you can. So RF over R1 equals VI minus VO over minus VI. Swap these two, right? If you couldn't do the algebra, just trust me for now. Yeah. So what's next? VI over minus VI plus VO over VI, which is minus 1 plus VO over VI. So VO over VI equals 1 plus RF over R1. That's the voltage gain of the non-inverting topology. Keep in mind it's different. So for the inverting topology, it's simply just the minus RF over R1. But for the non-inverting topology, there's no minus sign, so which means there's no phase change. So it's directly 1 plus RF over R1. Phase change, which means you got an input like this, right? Output becomes this. There's no phase change for the non-inverting. But for the inverting, this is the input, and here's the output. Amplify and phase changed. It's being inverted because of the minus sign over here. So that's the voltage gain for the non-inverting topology. Now let's see how we use it. How do we use it? Very quick note. So I think the best way to show you, not building on the board, but just show you on LT Spice. But you should know that there's some limits for LT Spice. Okay, to save time, I did this one idle time, right? So I think according to the lab instruction, what you need to do is a negative voltage first. You know how to do that? A negative voltage. Do it in case you can't do it. All right, I got here's a power supply, right? You got this and this and this, right? If there's two channels. So if if it requires plus 15 and minus 15, if you have two batteries, and you ground these two, because this 0 volts is given, right? You ground it to the common ground circuit. So it's going to be 0 volts. Keep in mind, 0 volts, 0 volts, 0 volts. If you short these two, right, and ground it. Okay. Because this battery, I told you can set it up, right? You can set it up as 15 volts. This is 15 volts. As I told you, if you set it up as 15 volts, it's going to boost the voltage from here to here as for 15 volts. Definitely, no, don't doubt about it. Okay, it's going to be 15 volts. So what's the voltage here? 0. So being boosted by 15 volts by the battery, what's the voltage here? Yeah, plus 15, right? What's the voltage here?
0.
Okay, and the battery is gonna, from plus to minus, it's gonna do what? It's gonna step this voltage down to, yeah. So now you can get plus and minus 15 volts. So from here, tell me which one is plus 15, which one is negative 15. That's the power supply, right? Sorry, this is red. Which one is 15, which one is negative 15 that you can use for your op-amp? It's very practical, right? So I'm just letting you know like which one you should connect to your plus, B plus, and which one should connect to the B minus to your op-amp. Remember, I just told you in here, the same circuit, the little battery here, the little battery here, right? And I shorted these two and grounded, right? So this becomes what? This becomes what? Got it? This is how you use it, okay? And now let's go through all these spice. Make it fast. We'll break for 2 minutes, okay? 2 minutes. So I don't want him to say anything.
So what comes out?
It's so bad because I get magically a little bit.
Wow, I didn't take it out. You guys
Because ready, we don't have too much time. Let's keep going, okay? So now imagine that you are connecting this one to on the breadboard, okay? So I'm going to generate a negative voltage here. I think the use is 15 volts. I'll directly put a negative 15 volts to make it easier. So I will rename it as V minus. Okay, so I got a 15 volts here and negative 15 volts here. And now it's okay to center the non-inverting terminal to 0 volts because you have plus 15, negative 15, so it's okay to swing the signal in the middle. You're not saturating, killing anything. You have a lot of room to the bottom rail. If you don't get it, just use it. It's okay. All right. So sine wave comes in, and I'm going to use 0 volts. Is okay for DC offset for the sine wave. So sine wave is going to swing around 0 volts in the middle. It's okay because I have plus minus 15 volts. And now the voltage comes in. It's so this is the load. I make it a big resistor. I just want to reduce the size of the load, right? So it's not drawing a lot of current. Okay, and then I have a 1 kHz. So let's just simulate it for 10 milliseconds instead of 100. Change it. Okay, run it. Okay, V in. Okay, V out. 10 times larger, 5 times larger than V in, and swinging around 0 volts. Okay. Questions? That's what we did on the paper, right? That's what you are expecting. Is there a phase change? The change to the phase. For input and output, is there a change to the phase? Yes, there's a change to the phase because they are not overlapping anymore. When you got a peak, you got a dip. You have a dip input, but you got a peak output. So there's a 180 degrees phase change. You know, it's okay if you don't get it, but there's a phase change. You can tell, right? You can tell. You can visually tell there's a phase change. So keep in mind the confusion will come later. And now, if I ground it, I don't have that negative swing, the room for the negative swing anymore. I ground it. I just put the bottom rail at ground instead of negative. So I don't have the room to swing negative. And I'm still centering that input voltage around 0 volts. Okay. I'm not using this one right now, okay? And what's gonna happen? In real world, what's gonna happen is, okay, so if you have your signal centered at 0 volts, you shouldn't ground your bottom rail. You should provide a negative room for the signal to swing. So what's gonna happen for this case is, it's gonna cut at the bottom. It's gonna saturate the bottom at 0 volts, right? It should, so this is the input, right? What you saw, right? And the input is still the input. It's not. It's before the op-amp. So if you probe it, still swinging around 0. But for the output, because it's going through the op-amp, which doesn't have the negative swing for the signal. So what's going to happen is it's going to amplify the signal. So when you have a tip, you have a peak, you have a dip, right? It won't be able to swing back to negative to me. It's going to cut here, and then. Yeah, so this is what you are getting. But if you do the LT spice simulation, it's the ideal op-amp. It will still do the job for you. Just let you know, it won't work in real world. Okay. So this is the two scenarios of this is non-inverting or inverting. Let me know. Inverting or non-inverting topology. V is going to where? The inverting terminal or the minus terminal. So this is inverting topology. Signal getting to the inverting terminal. And we just did a negative voltage bottom rail and a ground bottom rail. So if you want to make it work for the ground bottom rail, which is one of the tasks in the last instruction, you have to lift the signal to the middle, 7.5 volts. DC offset, you lift it so it's not swinging around 0 anymore. You lift it so it's swinging around 7.5. Why 7.5? Because it's 50% of the power supply. You put it in the middle so it has equivalent amount of room swinging to the top and bottom. And you also need to lift the non-inverting terminal as well. It actually shouldn't work, you know. I tried it before. I don't know why it works. But anyway, so let's keep doing how do you lift it. You know, let's lift it. You have to lift both sides, just let you know. And I'm going to just use, this is a voltage divider, right? I just use 10K, make it big so it's not consuming a lot of current. And I'll just connect this one to the middle. So it's dividing that VDD to 2 halves, which you are getting 7.5 volts here. So the lab tells you to use the potentiometer, 50K potentiometer. So you connect the potentiometer to this voltage divider. When you are connecting on the breadboard, you have to use a little screwdriver to twist it and probe it at the same time until you see exactly 7.5 on the multimeters monitor, and then you'll stop. Okay, this must be 7.5. You cannot just put a potentiometer there and you're assuming it's going to work. No, it won't work. Okay, this must be 7.5 volts, and we are talking about like zero, the ground as a bottom rail right now. Okay, it's different from the negative voltage. This is the ground at the bottom rail. We need to lift it. So we need to lift it here for the non-inverting terminal, and we need to lift the signal from the function generator. Just go to the DC offside option of the function generator and change it to 7.5 volts. You have to do it, both sides. How that works is called superposition. I don't know if I learned it in circuit 1, but it's superimposing a voltage to it. Don't dig too deep into it as well. Just use whatever, just do whatever I'm telling you to do. It's going to work, okay? Do this, take a picture or whatever. I'm going to upload it probably if you want to watch the video, and you have to do it, make it work. Okay, so this is inverting configuration. Inverting configuration. For non-inverting, I don't think the lab is asking you to do a bottom rail as a ground for the non-inverting because it's very complicated. I was thinking about it. It's impossible for you guys to finish it. You have to use a buffer. Not this one. But luckily, it doesn't ask you to do it. Okay, so if you have the V in going to the non-inverting terminal, again, you need a negative feedback, right? So that's the resistor network providing the gain. Okay, and then you are not grounding this guy. You need to lift it because you are grounding the bottom rail, so you need to lift it. You are lifting V in. I'm using 5 volts. That's why I'm lifting the sine wave, the V in, to 2.5 volts as a DC offside. So swinging around 50% of the rail, of the two rails. Okay, and I have to lift the other side as well. You are not grounding this guy. Okay, but how to lift it without affecting the resistance? Because if you put a resistor here, it's going to divide this resistance. It's going to fight a lot of things. So I have to put a buffer in here. This is called a voltage follower. It's a unity gain amplifier. It's just one. The gain is one, but you are isolating your voltage divider network from the gain resistors here. You have to do it in order to make it work. But luckily, the lab doesn't ask you to do that. I think for the inverting topology, I went through both the connections, right? You have a negative 15 bottom rail, you have a 0 bottom rail. I just showed you how to do it. And for the non-inverting, see, we'll scroll down. Okay, see here, part D, keep in mind, remember it. In part D, non-inverting configuration, construct a circuit, because everything here is like using a bottom rail for the ground. And then just suddenly, part D, which is the very bottom of the lab, is asking you to go back to figure 2, right? If you go to figure 2, it's a negative 15 volts bottom rail. It's easy, easy. You don't have to lift it. Don't worry about the lifting issue. I'll be around to help you guys out, okay? It's frustrating. I can finish the lab in 10 minutes, but I'll help you guys out, okay? Just give you guys some confidence. Someone can help.